Okay, so let's start our lecture today. So, yeah, so now we shall continue to study the residue theorem. Okay, so why the residue of this zeta z of this zeta naught is equal to 1. So, so let's start with the definition of this zeta z, right? So this zeta z is equal to let's recall the sum of this zeta z. So by definition, this zeta z is equal to 1 over z plus summation omega not equal to 0 of 1 over z minus omega plus 1 over omega plus z over omega square. Okay. So so let's separate the singular and non-singular part, right? So since this zeta naught is not equal to 0, right? So what we have is that so this is equal to let's pull out this zeta naught from this sums. So yeah, so let me try to make sure that I get the right idea here. So okay, so because this choice of A is arbitrary, right? This choice of A is arbitrary. So let's say that this A is let's say that this A is away from the 0, right? So because okay, so let's say that this A is away from 0. Okay. A is away from 0 such that this zeta naught is not equal to I forgot what is exactly the zeta naught. I think let me try to make sure. Okay, yeah. So this theta naught is the lattice point inside this parallelogram, right? So, okay, so that's that this theta naught is not okay, so yeah, so this theta naught is exactly the lattice point, but not equal to 0. Okay, so okay, let's say that this A is away from 0. Okay. Okay. And then what we have is that we have so this zeta z is equal to 1 over z minus zeta naught plus 1 over zeta naught plus z over z minus plus z over zeta naught squared plus 1 over z plus summation of omega not equal to 0 of not equal to 0 and this zeta naught, right? Of this guy. Omega plus z over omega squared. Okay, so so here what we have is that so here if we want to compute the Laurent series expansion, right? So okay, so the question is that yeah, so what is the Laurent series expansion of zeta z at this zeta naught? So yeah, so what is the Laurent series expansion of this zeta z and this as zeta naught? So so what is the Laurent series expansion?
So let me check the notes for my complex analysis class. God is absolutely. Okay, so
Okay, so so let's do this one. So let's the like aim the Laurent series expansion of this zeta, the zeta function at the point zeta naught is 1 over z minus zeta naught plus plus yeah, so plus some so n from 0 to infinity of an times z minus zeta naught to the nth power. Okay, so the reason for that is because except this part, right? So so the proof is that so maybe let's say the claim, okay. So okay, so since since the function let's just separate this function away from the else part. Okay. So basically the idea is that I want to show that basically these functions, they are just because for this omega other than this 0 and zeta naught, right? So this 1 over z minus omega, it is well defined around a neighborhood of this zeta naught, right? So this means that everything else here is holomorphic near this zeta naught, okay, and this is holomorphic near zeta naught, and this is also holomorphic near zeta naught. So basically, if you take a limit of holomorphic function, and the convergence is also so what is the convergence? So yeah, so the convergence so the convergence is guaranteed by the absolute summability, right? Yeah, so the convergence is guaranteed by the absolute summability because except for like finitely many terms, we know that the tails behaves like 1 over z cubed or something for this one, which is converging. Yeah, so even though we pull out this term, so the rest of the term, because after we pull finitely many terms, the finite the tail behaves like 1 over z cubed. So the finite term doesn't matter because it will converge anyway, and the tail will always converge. So this guy will converge absolutely. So then absolute convergence means that it will conditionally converge, and then the limit is always the same, no matter how we change the order, right? So therefore, so let's define this f of w. So maybe let's use this one. So the function 1 minus, so 1 over z minus omega plus 1 over omega plus z over omega squared. Is holomorphic. Wait. Yeah, so basically my goal is to conclude that okay, let's say this one. It's homomorphic on a neighborhood of zeta naught, right? For any yeah, I should say for any omega in, okay, so let's say this. So for any omega in this lattice point, minus minus, so here I think in the past I used this notation to denote the lattice point including the zero, right? So yeah, so either way, so like so here for the notation issue, so I will use this lattice point minus 0 and also zeta naught. Okay. So for any omega in this guy, the function this function is homomorphic on a neighborhood of zeta naught. Okay. So yeah, so basically I want to set up the uniform convergence on compact subset. So let's say neighborhood u of omega zeta naught, right? So let's denote this neighborhood by u. Okay. So let's see. So basically what I'm aiming for is that so what I want to show is that partial sums. So again, in order to figure out, like for better notation, I want to use I want to use a enumeration of this lattice point. Okay. Let omega n. Okay, so here maybe I want to use a different notation here. So let omega n be a enumeration of instead of all omega in this omega in wedge minus 0 and zeta naught. Okay. And then if you take the limit as n goes to, yeah, so let's just say that the function the sequence of partial sums n from 1 to capital N of this 1 over z minus omega n plus 1 over omega n plus z over omega n squared. So the sequence of partial sums n from 1 to infinity converges locally uniformly, converges uniformly, okay, on compact subset of U. Okay, so how do I show this one? So okay, I think there's a previous argument that I made about this one. So yeah, I think there's an equality that I used before for this one. So so I think I let R to be yes. So yeah, so let me see. So So okay, so here is a statement that I used in the past. So let's see. So yeah. So let's see. So 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 this is what I showed before. So showed before that so fix any r bigger than 0. So if we have modulus z is less than or equal to r, and modulus of omega n is bigger than 2r, then yeah, so then we have that modulus of 1 over z minus omega plus omega n plus 1 over omega n plus z over omega n squared, which is less than or equal to 2r squared over omega n cubed. Okay. Okay, so and then so yeah, so let's talk about let's talk about the idea of why the why the so let's talk about why the because I think I have to leave now, but so I think this so next time I will next time I will try to I'll try to discuss on how this converges on common subset. Okay.